We're now going to look at this carbon-carbon bond rotation in ethane from the perspective of energy. So if you recall from the last video, we were looking down the carbon-carbon bond, and we started with ethane with these two blue hydrogens lined up. And then we started going through rotations, and so we rotated 60 degrees to get this structure 2, and then 3, another 60-degree rotation, 4 again, 5, 6, and 7. And so what we were tracking was what we called the dihedral angle. Here we said it was 0. Here it went to 60. Here it went to 120. Here it went to 180. Here 240. Here 300. And then finally here all the way back around, and this was a 360. And hopefully by now you've been able to pick up on a pattern that's emerging. So if you look at the structures that we labeled 1, 3, 5, and 7, you notice that in every one of these, all of the atoms are lined up directly across from one another. And when this happens, we call this interaction eclipsing. So my hand's in the way there. But we say that these are eclipsing interactions. And what we're looking at here is called the eclipsed. These are eclipsed conformations of ethane. The word conformation means that it is the same molecule, but just has rotated about one or more bonds. And so you're looking at it at these different rotational places in space. And so it's the way that the molecule has arranged itself in 3 dimensions. And so in the case of ethane, one possible way of arranging is in an eclipsed conformation. The other 3 conformations that we've looked at, that we labeled 2, 4, and 6, notice that everything is actually separated, and this is what we call the staggered conformation. Okay, so this is staggered. These are all staggered conformations. So let's go back and look at these eclipsed conformations. And let's talk about this idea of eclipsing a little bit. So if you take a look here, there are 3 what we're going to call HH eclipsing interactions. And each of these costs about 4 kJs per mole, kilojoules per mole. So this means that in order for ethane to undergo a rotation, it's going to have to pass through an eclipsed form, and in order for it to do that, it needs to have enough energy. It needs a total of 12 kJs per mole because there are 3 such interactions that must take place. So in order for ethane to even go through this conformation at all, there has to be 12 kJs per mole available energetically. If it's not, it will just kind of get stuck as it is, and the rotation will not take place. Notice if we go back and look at the staggered conformations, there is no eclipsing. And so each one of these staggered conformations are 12 kilojoules per mole lower in energy than any eclipsed conformation. So if we were to do a plot of the energy as we proceeded through a full 360-degree rotation about the carbon-carbon bond, and we plotted the energy versus the dihedral angle, say of the 2 protons that we were tracking before, you'd see that it's going from, we start off at a 0-degree dihedral angle in an eclipse conformation 1, then it goes to a staggered conformation 2, back to eclipsed 3, staggered 4, eclipsed 5, staggered 6, and then back at the 360 dihedral angle to another eclipsed conformation 7. If we were to plot this energy out and generate a curve, you would see that we get a sinusoidal shaped curve, and the difference between the maxima and the minima is going to be 12 kJs per mole. And that's a reflection of these eclipsing interactions that are taking place up here. The last idea that we need to talk about is, why does this eclipsing cost energy? And as we know, electrons do not like to be near one another. They don't like to occupy the same space. There's a repulsion there. And so when they have to be lined up directly like this, when you have 2 sigma bonds across from one another, there's a sigma-sigma electron repulsion. And it's this repulsion that costs 4 kJs per mole. Of course, when you multiply that by 3, you get a total of 12 kJs per mole total, because this is happening 3 times. And this type of strain, this type of repulsion that you're seeing, is what we call torsional strain. So torsional strain is sigma bonds that are across from one another, and you get this sigma-sigma electron repulsion that takes place.